Welcome to AI Paper Slop. Today we are looking at the paper, When Does LeJEPA Learn a World Model? By David Klint, Jan LeCun, and Randall Belstriero.
Yeah, this is a massive one.
It really is. So we are getting straight into the core insights right now. For years, self-supervised learning has shown empirically that joint-embedding predictive architectures, or JEPAs, learn these incredibly robust representations of the world.
Right, they just work, but we didn't really know why.
Exactly. But this paper finally proves why, mathematically, and the key takeaway you need to know is this. LeJEPA, which uses an alignment loss combined with an explicit Gaussian regularization called SIGREG, can linearly recover the world's true latent variables from totally scrambled, highly nonlinear observations.
But there's a huge catch there, right?
Oh, a massive catch. It achieves this if and only if the underlying true variables of the world are Gaussian and evolve under additive noise. The authors basically flip classical independent component analysis, or ICA, entirely on its head.
Yeah, they prove that while a Gaussian distribution famously breaks linear ICA, it is actually the unique, mathematical skeleton key that makes nonlinear representation learning identifiable.
It's just wild.
It's a huge leap from, empirical alchemy to structural certainty. We are taking this wildly successful training recipe and finally building a concrete mathematical floor underneath it.
Right.
For the first time, we have a structural guarantee defining what a valid world model actually requires.
So to understand how LeJEPA reverse engineers the world, we first have to mathematically define what the world actually is.
Yeah, what are we even recovering?
Exactly. The authors include this great footnote referencing Plato's cave, but let's make it a bit more visceral for you listening. Imagine you have a perfectly organized filing cabinet.
Okay, like that.
Every folder is a distinct, independent variable of reality. Say the precise XYZ coordinates of objects in a room. That's our true latent state Z. Now, a tornado rips through the office.
Yeah.
Right, the folders are shredded, the papers are scattered into this chaotic, overlapping pile on the floor. That pile of paper is our data, X. The tornado is the generative function of the universe, which we'll call G.
And our neural network's encoder, F, has to look at that chaotic pile of paper on the floor and somehow mathematically reconstruct the exact filing cabinet.
Precisely. But to even prove that's possible, the paper has to set some ground rules about how the filing cabinet behaved before the tornado hit.
Right, and those ground rules dictate the transitions between positive pairs.
Yeah.
In self-supervised learning, positive pairs are just two views of the same underlying reality, like two consecutive frames of a video.
Got it.
So to even get this proof off the ground, the authors assume three fundamental properties about how the true latents transition from frame 1 to frame 2.
And those are?
First, independence. The latent variables don't interact with each other, and their transitions are totally decoupled. Second, stationarity. The overall probability distribution of the world doesn't shift between frame 1 and frame 2.
Yeah.
The physical laws just stay constant.
Right, gravity doesn't suddenly turn off.
Exactly. And third, additive noise.
Wait, let me make sure I'm picturing this right. By additive noise, are you saying the next state of the world is just some function of the current state, plus a completely random, independent injection of randomness?
That is exactly it. It's the classic assumption of physical diffusion. But the magic happens when you combine those three transition rules with the assumption that the latent variables themselves are Gaussian.
Oh, right.
Yeah, if you enforce independence, stationarity, and additive noise on a perfectly Gaussian world, you restrict the universe's physics exclusively to what is known as an Ornstein-Uhlenbeck, or OU, process.
Okay, for the ML engineers tuning in, let's synthesize what an OU process actually looks like. Conceptually, it just means the next state is a decayed fraction of the current state, plus some fresh Gaussian noise, right?
Yeah, pretty much.
There is an autocorrelation parameter, let's call it rho, that acts like a memory.
You've got it. The parameter rho sits strictly between 0 and 1. It pulls the state back toward the center, preventing it from just wandering off to infinity, while the additive noise keeps it constantly buzzing.
Right.
It is an autoregressive process that perfectly preserves the Gaussian shape of the world over time.
And this is where we tie it back to the code. Think about what LeJEPA is actually doing in PyTorch. It has an alignment loss trying to pull the embeddings of two different video frames closer together.
Right, the standard JEPA objective.
But simultaneously, it has the SIGREG term, which stands for shifted inverse gamma regularization, forcefully molding the entire embedding space into a perfect Gaussian distribution. The network is being mathematically bullied into acting like this exact OU world you just described.
That tension is the entire mechanism.
Right.
The network is regularized to enforce that Gaussian geometry. But the real question, and what the authors address in Theorem One, is whether forcing that specific geometry actually compels the network to untangle the tornado's mess.
Well, let's dive into Theorem One then. How on earth does an alignment loss in a Gaussian shape force a neural network to find the true untangled variables?
We have to analyze the system through its spectrum.
Yeah.
When LeJEPA minimizes the alignment distance between the embeddings of two views, it is mathematically identical to maximizing the correlation between them.
Okay.
Because we established our true world follows a Gaussian OU process, the transition operator, like the mathematical engine mapping state A to expected state B, possesses a very specific set of eigenfunctions.
Okay, an eigenfunction. For those of us who haven't taken linear algebra in a few years, let's visualize this.
Yeah, it can be dense.
Is it fair to think of an eigenfunction like a specific frequency or a shape that manages to survive the transition without getting distorted? It just gets scaled up or down by a constant multiplier, which is the eigenvalue?
That is a perfect way to visualize it. It's a structural feature that preserves its identity. For a Gaussian world evolving under an OU process, those eigenfunctions are universally known in closed form. They are the Hermite polynomials.
Ah.
You can think of them as the natural orthogonal basis for Gaussian variables. Degree 1 is a purely linear function, degree 2 is quadratic, degree 3 is cubic, and so on.
So any complex feature your neural network decides to learn can be decomposed into a weighted sum of these Hermite polynomials.
Exactly.
And this leads to the most brilliant part of the proof. The eigenvalue for a degreed Hermite polynomial is exactly our autocorrelation parameter, rho raised to the power of d.
This is the critical mechanism. Remember that rho is a fraction between 0 and 1.
Right. So let's say rho is 0.9. If the network learns a purely linear feature, a degree 1 polynomial, the correlation across the two views is just 0.9 to the power of 1, which is 0.9.
Yep.
But if the network gets clever and tries to use a quadratic feature, the correlation drops to 0.9 squared, which is 0.81. If it uses a cubic feature, it drops to 0.729.
It just keeps dropping.
Exactly. Because rho is a fraction, the math inherently brutally punishes higher degree nonlinear polynomials. The higher the degree, the faster the correlation decays.
And remember, the network's objective function. Its only goal is to maximize correlation across the positive pairs.
Right. It wants that number as high as possible.
Because any nonlinear distortion introduces higher degree Hermite polynomials, and those higher degree polynomials strictly reduce the overall correlation, the network is trapped. The only mathematical way to achieve the absolute minimum loss is to drop all nonlinearities and rely 100% on the degree 1 linear Hermite polynomials.
Meaning the learned representation has to be a purely linear map of the true latents. The alignment loss acts like this. Violent low-pass filter aggressively scrubbing out all the high-frequency nonlinear garbage that the tornado introduced. It's forced to just find the linear rotation of the filing cabinet.
Because of the SIGREG constraint keeping everything Gaussian, it's not just any linear map, it is strictly an orthogonal rotation. The network untangles the complex manifold simply because nonlinearities offer a terrible return on investment for the loss function.
That is such an elegant piece of theory, but it immediately begs a massive question. So we know a Gaussian world works perfectly, but what if the world isn't a perfect bell curve?
Right, reality is messy.
Does the whole system collapse, or is there another shape that works? This brings us to Theorem 2, and honestly, the history here feels like a paradox.
Oh, the irony is inescapable if you know the history of source separation.
Right, because in classical linear independent component analysis, the Gaussian distribution is famously the one shape where the algorithm completely fails.
Total failure.
A Gaussian distribution is perfectly symmetrical. It's a featureless sphere.
Yeah.
If you try to do linear ICA on a Gaussian, there are no corners or edges for the algorithm to latch onto, so it can't figure out the original axis.
Yeah.
Yet here, in nonlinear representation learning, we are saying we need it. Why does nonlinear ICA demand the exact thing that breaks linear ICA?
Well, to resolve that paradox, we have to look under the hood at Sturm-Liouville theory. When you have a latent variable evolving under constant diffusion, which is our additive-noise assumption, the transition operator is governed by a Sturm-Liouville differential equation. A universal property of these equations is that the first non-constant eigenfunction is always monotonic.
Okay.
It always goes in one direction.
Yeah.
That alone gives you identifiability up to a monotonic transformation.
But monotonic isn't strict enough for a world model. Monotonic just means the order is preserved. It could be wildly stretched or compressed like a funhouse mirror. We want linear identifiability.
We do.
We want to be able to slap a simple linear probe on the embeddings and perfectly read out the state of the world.
Right, and to get linear identifiability, we must demand that this first eigenfunction isn't just monotonic, it must be perfectly affine, perfectly straight.
Okay.
And forcing that eigenfunction to be straight places an extreme, non-negotiable constraint on the underlying probability distribution. It restricts what is called the score function.
Let's break down the score function for a second. If I'm visualizing the probability distribution as a topographical map, like a mountain, what does the score function represent?
Good analogy. The score function is the gradient of the log probability. On your topographical map, if you are standing somewhere on the side of the mountain, the score function is the vector field, telling you exactly which direction points the absolute peak and how steep the slope is to get there.
Got it. So if we mathematically demand that our eigenfunction is a perfectly straight line, what does that do to the mountain?
It forces the score function to be linear. It means the slope of the mountain must change at a perfectly constant linear rate as you walk away from the peak.
Wow.
Yeah. And when you solve that specific differential equation, when you ask the universe, what is the only probability distribution where the log derivative is a perfectly linear function?
Yeah.
Only one shape survives the math.
The Gaussian bell curve.
The Gaussian. Theorem 2 formally proves that among all possible worlds with independent, stationary, additive noise transitions, the Gaussian distribution is the unique, singular shape that guarantees linear identifiability.
That is mind-bending. The very featurelessness that makes a Gaussian impossible to solve in linear ICA is the exact structural glue that makes it the only solvable shape when you are dealing with horribly nonlinear neural networks.
It's beautiful, isn't it?
It really is. For the ML engineers listening, the takeaway here is stark. If your true world variables follow a heavy-tailed distribution or a flat uniform distribution, and you try to learn a linear world model, the math says you can't.
Yeah, you just can't.
You are mathematically blocked from perfectly untangling the state space.
Your network will do its best, but it will always leave some nonlinear entanglement behind.
Okay, beautiful math at the global minimum. But we both know that when you actually fire up PyTorch or JAX, the global minimum is a myth.
Oh, absolutely a myth.
We have finite batch sizes, messy gradients, learning rate schedules that never quite settle. Does this elegant theory actually survive the brutal reality of empirical deep learning?
That's exactly what Theorem 3 addresses. It bounds the recovery error when the network only approximately solves the objective. The theorem breaks the error down into two competing forces.
Okay, what are they?
The whitening error, which we call epsilon, and the alignment gap, which we call delta.
Let's define those. Whitening error, epsilon, is just how far your learned embedding space is from a perfectly spherical identity matrix.
Right.
And the alignment gap, delta, is how far your alignment loss is from the theoretical absolute floor. I imagine one of these is much, much harder for gradient descent to close than the other.
Emphatically, yes. Pushing a covariance matrix toward identity, minimizing epsilon, is relatively easy for a modern neural network. It's just spreading out the batch.
Right.
But perfectly aligning positive pairs through a massive nonlinear encoder that requires physically untangling the manifold. That is exceptionally difficult.
It's the difference between smoothing out a crumpled piece of paper versus trying to perfectly unweave a knotted sweater.
Exactly. In practice, the alignment gap, delta, entirely dominates the error bound. The crucial takeaway for practitioners is that the training loss itself, specifically that alignment loss, acts as a highly reliable proxy for identifiability.
So if your loss is going down, you're good.
Yep. If your alignment loss is steadily dropping, you can be mathematically confident your model is actively untangling the true state of the world.
And the authors didn't just prove this on paper, they built some truly vicious 2D toy problems to watch it happen.
Oh, they were nasty.
They really were. They didn't just lightly blur the data. They took a neat 2D circular Gaussian distribution and ran it through norm-dependent spirals, sinusoidal shears, and even a real NVP-style coupling layer.
Yeah.
They turned the true state into an unrecognizable swirling galaxy of data points, and LeJEPA completely reverse-engineered it. It untangled all of them back into perfect Gaussians.
Toy problems are great for intuition, sure. But the real empirical test was their 1024-dimensional scaling experiment.
Right, that's where things usually break.
Exactly. They tested 3 different objectives to see what survives at scale. SCREG, which enforces full Gaussianity. ViCREG, which only enforces variance and covariance, and info in C, the dominant contrastive learning objective that almost everyone uses.
Let me guess. Info in C hit a wall.
It didn't just hit a wall, it collapsed.
Wow.
Yeah. Both SIGREG and ViCREG maintained an R-squared recovery score of over 0.999 all the way up to 124 dimensions. They scaled flawlessly. But info in C degraded severely as dimensions increased.
Wait, why does contrastive learning die here? Contrastive loss is the backbone of so many vision language models.
It comes down to the curse of dimensionality on the estimator. Info in C relies on a fixed-width Gaussian kernel to measure similarity between positive and negative samples.
Okay.
In 1024 dimensions, the Euclidean volume expands massively. The distances between points grow so large that the similarities inside that fixed kernel underflow to absolute zero.
And when similarities hit zero, the gradients vanish.
The gradients simply die. The network stops learning. It's not a failure of the fundamental theory of contrastive learning, but a mechanical failure of the batch statistic estimator at high dimensions.
That makes total sense.
Yeah, explicit regularization methods like SIGREG don't suffer from this kernel collapse, which is why they scale so beautifully.
Okay, so we've proven it works on math problems, and we know SIGREG scales to high dimensions. But the ultimate boss fight for any world model is raw pixels in a reinforcement learning environment. Let's look at the DeepMind control Reacher experiment.
This is where the theory violently collides with reality. The DMC Reacher environment is simple. It's a robotic arm with a 2D latent state, the angle of the shoulder joint and the angle of the wrist joint.
Right.
The researchers trained a convolutional neural network encoder from raw 64 by 64 pixel image frames. But they set up two entirely different data collection paradigms.
Condition 1, they generated the image frames by manually sampling the joint angles using the exact mathematically perfect Gaussian-Ornstein-Uhlenbeck process we talked about earlier. Basically, a drunk robot taking a perfect random walk.
A very mathematically precise drunk robot.
Exactly. And condition 2, they used real trajectory frames generated by a fully trained soft actor critic, or SAC, reinforcement learning policy, a highly competent robot performing its job perfectly.
The contrast in the representation learning is staggering. When trained on the drunk robot's random walk, the OU condition, the encoder, achieved an arc squared of 0.95. It successfully reverse-engineered the raw pixels and recovered a linear representation of the true shoulder and wrist angles.
But the expert data, the SAC trajectory.
Total failure. The R squared never exceeded 0.5. The network completely failed to linearly untangle the joints.
That feels incredibly counterintuitive. We usually assume that high-quality expert data yields better models. Why did the expert data completely nuke the representation?
Because expert, goal-directed behavior inherently destroys the fundamental mathematical assumptions we spent this whole time establishing.
Oh, I see.
When a SIC policy is trying to solve a task, it drives the robotic arm to a specific target and aggressively keeps it there. Think about what that does to the marginal distributions.
It's no longer a smooth bell curve. The wrist angle is probably constantly maxing out against its physical limits, creating a uniform distribution of states. And the shoulder angle is just hovering around a single point with massive heavy tails when it gets bumped.
Furthermore, the behavior becomes highly anisotropic. The shoulder and the wrist are moving and correlating at completely different task-dependent rates.
Right, the math breaks.
The math of Theorem 2 requires the environment to explore state space like an isotropic random walk. By imposing a goal-directed policy, you obliterate the Gaussianity and the isotropy that makes linear identifiability possible in the first place.
This is a massive warning sign for the entire field of robotics and RL. If your pre-training strategy is just to slurp up millions of hours of expert trajectories solving a specific task, you are actively shooting yourself in the foot.
You really are.
You are breaking the Gaussian assumption. By training on highly optimized behavior, you are mathematically preventing your world model from learning the true underlying physics of the environment.
It fundamentally changes how we need to think about data collection for self-supervised control. If you want a generalized world model, you need unstructured isotropic exploration data.
Let's tie a bow on this. This paper isn't just an abstract proof, it has massive engineering implications. Because of what they outline in Theorem 4, if you achieve this linear identifiability, if you get the data right and use LeJEPA, any orthogonally invariant cost function transfers from the true world to your learned latent space perfectly.
Which means you can do latent space planning. You can simulate the future entirely inside the neural network's embeddings, find the optimal path, and the math guarantees that your internal plan will execute optimally out there in the physical world.
It's the holy grail of model-based RL. It proves that under the right data conditions, LeJEPA doesn't just learn a useful representation. It is mathematically forced to learn the correct representation.
It is a remarkable piece of work that finally gives us a rigid framework for evaluating representation learning architectures.
Absolutely. Thank you for tuning in to AI Paper Slap today. We love dissecting these proofs with you. But before you go, I want to leave you with a final, slightly provocative thought to mull over. We just spent this entire deep dive proving that building a mathematically correct, linearly identifiable world model strictly requires continuous Gaussian latent distributions and isotropic transitions.
Right.
So what does this mean for large language models? LLMs operate entirely in discrete token spaces. Words, concepts, and syntax trees are decidedly not isotropic Gaussian random walks. Are we fundamentally lacking a mathematical equivalent of the Gaussian prior for discrete reasoning? And until we find it, will our language models always be doomed to slightly scramble the true causal structure of the world? Think about it. See you next time.